if you're okay with it, we'll post it publicly. Okay, you're asking. Yes, absolutely. All right, I hope I cried. I think you're ready. Thank you.
Okay. Hi, everyone. I think we're at time, so we're going to get started. I'm Chris Heckman, Associate Professor in this department, and it's my pleasure to introduce Dr. Danna Gurari, an Assistant Professor also in this department, and the Director of the Image and Video Computing Group. Before joining us here at CU Boulder, she was also an Assistant Professor at University of Texas at Austin and earned her PhD with Margaret Bettke at Boston University. She's earned multiple Best Paper awards at some of the top venues in her field, Pi and WACB being two. Her research is supported by major funding from the National Science Foundation, Chan Zuckerberg Initiative, and Microsoft, as well as other companies. On top of that, her work has also been featured in popular publications like Wired and TechCrunch. Today, she will be presenting Designing AI to Empower People. So please join me in welcoming Dr. Gurari.
Thank you. Thank you, Chris, and thanks for everyone for being here. Let me just turn up the volume a little bit. Great. So, there we go. So the goal today is about enhancing humans' capabilities with AI-based solutions. There is a lot of discussion about replacing in the future, and I'm happy to have those conversations after the discussion today. But for now, we're just talking about enhancing humans' capabilities. And a lot of my inspiration has come from authentic use cases with visual data. And so I want to introduce three characters who embody what inspired quite a bit of my work. I'll call one Eric, who is a blind person. Another I'll call Zoe, who is a basic science researcher. And another I'll call Benjamin, who's just a lay person. Eric has gotten used to, with his phone, taking a picture, optionally recording a spoken question, and having that sent off to people who, in turn, will be able to provide either a description of that image, called caption, or an answer to the question. Zoe is a basic science researcher who spends her day collecting data and looking through microscopes, trying to find some kind of information that tells us how the body works, such as how do cells make up blood vessels. And Benjamin just likes to have some fun in making images. That could be for a variety of reasons, including for creating marketing material, creating artwork, finding exemplary images for blogs, websites, design presentations, and more. And Benjamin can do this right now through, for example, finding a photographer, whether himself or hired, to go and take the pictures he's trying to capture. Or can go and look on stock photo websites, which there are plenty of options, including Shutterstock, Unsplash, iStock. And the key AI problems are a lack of representation and efficiency in representing those use cases. So I'm going to talk about the AI solutions that improve representation and efficiency. And that will include dataset challenges for more inclusive models, humans in the loop for practically useful results, and finally, resource-saving methods for less costly, faster AI training and inference. So diving in, the first part of the talk is going to be about my team's work on dataset challenges for more inclusive models. Sponsors are on this slide. And the idea of this work is to accelerate progress by creating community. Prior to 2009, many people who were developing AI models would go and create their model and find the data set that showed the best of the model. It was like this perfect marriage. Typically, someone could curate about tens to hundreds of examples. But starting in 2009 later, there was a major shift that was inspired by this thing called crowdsourcing, where you can pay anonymous people on the web to go and annotate data for a small fee. And so, starting around 2009, we started to have an explosion of dataset challenges that were created. And these became more large scale, having thousands, tens of thousands, hundreds of thousands, and even more of labeled examples. And the idea of these dataset challenges was like taking a test. Who here has taken a test? Excellent. So you know what I am talking about. You have the questions and you know what the answers are, and hopefully the instructor told you how they are going to grade the test, right? So that's the idea, is we put out a challenge that is a test for AI. And sometimes when we give that test beforehand, we will give them some training material. The essential ingredients for each dataset challenge is to have test examples that include what are the target results, a metric for assessing the similarity between each model prediction and the target result, and new challenges for the community to tackle. Because if a test is easy, then it doesn't really push the community forward. It's not a challenge. And so there has to be something new and hard that models that exist at the time that the dataset challenge is released has not yet been solved. So my team has been a big part of this for almost a decade. We have created 22 dataset challenges that are inspired by authentic use cases. And I just want to share about 2 key contributions of our work in building dataset challenges. The first contribution is we have been putting out the first publicly available image description datasets that originate from authentic use cases. What do I mean by image description? If you have an image, you can do something like create a caption, a bunch of small light brown mushrooms in a green field. Or you could answer a question about that image, such as, is it edible or poisonous? Answer, poisonous. The source for this data set that we built from was created by Jeff Bigham, a collaborator of mine at both Apple and Carnegie Mellon University. And he had created an app which went viral. Between 2011 and 2015, over 72,000 requests were submitted by over 11,000 people using this application. Originally, Jeff and his team members were answering questions and providing descriptions, and eventually they said, hey, we'll go employ crowd workers on the web. We need to be able to also do our job and support these users. For 62% of those requests, users agreed to anonymously share their data publicly. So publicly sharing authentic user data for the 44,799 submissions we had required some unique steps because these were authentic data sets. One part of it is anonymization. We had to transcribe the questions to remove people's voices because that can be identifying of who are the people. We also received images to remove metadata such as the location where those images were taken. And then we did filtering to remove all personally identifiable information such as faces, prescription pill information, stuff in mail like bills. We had credit cards, we had passports, you name it, it was in the data set. And then with that data, we would annotate it for each one of our dataset challenges. Often when we created one, there was 4 steps and we open sourced the tools. The 4 steps are create the annotation tool, create the instructions, create quality control process, connect to AMT and crowdsource. While I will spend little time talking about creating instructions, I'd like to highlight that's probably one of the hardest steps, is how do you get someone to do a task and do it well. The first dataset challenge we created was for visual question answering. Here is just what the task is. Given a question such as what color socks are these, someone needs to type in the answer. What are issues that could go wrong? You can have spelling errors, you can have people that spam. We had a lot of cleaning up we had to do, but that was a task. So if we ask what color socks are these, what might you answer? Black. So everyone I heard just agreed. We collected 10 answers per visual question because it's not always a given that people will agree. That resulted in 311,730 answers that we paid crowd workers $2,182 for. Next up, our task was captioning. Here's some of the instructions that are shared, including your description should contain at least 8 words. Much of the last task and this task were based on instructions that came from the people before us who had developed these data sets. We just borrowed their code bases. And so we only made slight tweaks, such as adding quality issues are too severe to recognize visual content, and tailoring also saying that we should describe parts of the image that might be important to a person who is blind. We collected 5 captions per image to see some kind of agreement for our ground truth. And that resulted in almost 200,000 captions from 1,623 annotators who spent 3,736 hours annotating, which is equivalent to 93 40-hour work weeks. We spent considerably more than the previous task. In this one, we spent $21,828. In that task, we also collected labels indicating if text was present. Someone answers yes or no. And that helped us spawn another challenge, which is binary classification. Is there text in the image? Additionally, we asked people to tell us what is the quality issues of the image, if anything, such as is it blurry, is it too bright, is it too dark? And with that, we were able to make also a dataset challenge for predicting what are the quality issues where there can be multiple in an image. And then lastly, just exemplary of many of the dataset challenges we have is locating content. In this case, it was what was the most salient or prominent content in the image. And so this is an example of a basic user interface where someone draws with clicks around the content that is the most prominent content. In this case, we collected 2 segmentations per image, collected over 74,000 segmentations from 40 annotators who now we consistently go to because they have been very reliable. And we spent $13,152 for their 1,290 hours of work. Okay, so it's just a little bit of a highlight of what goes into creating these data sets. But who cares about these data sets if they're not a challenge for the community, right? There has to be something that's challenging for the community to rise up and try to solve. What happened from the inception is we offered many things that were challenging. One was that our data set was relatively small, and that resulted in relatively little or no training data for many of our challenges. So if you look at our data sets, they had somewhere between 30 and 40,000 images after filtering out content. As I mentioned, crowdsourcing enabled us to create very large data sets when we were working in contrived settings where we could just download images. So our data sets were very small compared to what else has been created. Additionally, Viswiz's authenticity, being grounded in real use cases, resulted in the images and the questions looking quite different from mainstream data sets. Many of the images are low quality. We found 51.6% were flagged as having some kind of quality issue. We found 63% of the images contained text. Prior to this challenge, people were not really looking at text-based issues. The existing data sets that had been created were almost all based on grabbing images from the web based on some kind of term like dog, cat, bus, car. And those often lacked text. And when our data set came out, the community realized these matter in practice and started to grow around text-based data sets. Many novel concepts were in our data set because we weren't downloading images from the web based on certain topics, but rather capturing things that were in people's real lives and their day-to-day lives. We were getting things like thermostats, currency, and progresso. Thoughts, if you didn't know. And lastly, many of the images contained private content, specifically 12%. Many of the questions were unanswerable, 29%. So what is the expiration date? The answer is not in the image. Many asked about private content. 2.5% of the questions were asking about private content, such as what is the medicine in this pill bottle? I have removed that private information, and that's the case for what's publicly available as well. And many of the questions asked about very large, often salient image regions, which was not happening in mainstream data sets. If you think about why might that be, if someone's blind and they're trying to learn about something, they know what they want to learn about. And they take the thing that they're trying to learn about, they put it in front of the camera, and they take a picture. Or they put it somewhere where they know. And so often you're getting the thing of interest is very large. After the Viswiz dataset, we put out another dataset, which is the second and only dataset that exists that is from an authentic use case and a dataset challenge, I would like to say, from an authentic use case. And this was sourced from Stack Exchange. Who here has used Stack Exchange? Okay, so many of you. So maybe you've seen some of the data in our data set, but we crawled the internet from Stack Exchange site, collected 64,696 of the examples, which had an image with a question about it. And then we also pulled the answers. So unlike the VisWis dataset, where my team went and created annotation interfaces to produce answers, in this case, we didn't have to do that because the answers were already provided within Stack Exchange from the people who responded to the original question, such as what is the history of this coin? If you compare some examples from what existed before the dataset was released, we have the VisWis, we have this one, which was the pioneering dataset. What is the mustache made of? This is the VisWis dataset. Does this foundation have any sunscreen? And another relevant dataset. But hopefully it should pop out that the length of the answers in this new dataset are dramatically different than what existed at the time. At the time, the dataset challenges typically resulted in 11 or fewer words in the answers. Because part of making a test where we could grade the answers was asking annotators to give us short answers. The techniques for how to evaluate were very difficult if we had long answers. But what you find is that in practice, at least on Stack Exchange, longer answers are standard. And if you go and you ask people who are blind what they want, which is something we did, I don't have a slide about it, but you will also learn that the blind users also often want longer answers. And I like to just note that more generally, when we create many of our data sets, we try to represent some kind of new domain. And so, as I mentioned, we've looked at biomedical engineering stuff. And so we have also put out a data set for tracking in videos cells. And it just offers a new domain for people who are working on tracking algorithms. And in this case, we had covered larger and more diverse scenarios. So our data set was much, much larger, and we just covered many more cell lines. Okay. Our second contribution on the dataset creation front is for novel AI tasks. And there are two main themes when we are proposing novel AI tasks that had not been proposed before our team. One theme is around ambiguity. Another is around privacy. Start with privacy first. When we look at the VisWis images, as I mentioned earlier, 12% of those images had some kind of private content in them. And 62% of those examples that had a paired question were asking about the private content. And so if we want to preserve privacy, we need to understand if someone's question is asking about the private content or not to decide whether we should obfuscate, remove the private content or not. And so we put out a novel task, which is decide given a visual question, so the image and the question, whether that question is asking about private content or not. So what is medicine in this pill bottle? The answer would be yes, someone's asking about that private information. But an extension of that is if someone just wants to know something like what is the medicine in this pill bottle, they don't need to be able to read everything else that's on that pill bottle, right? All they want to know is one piece of information. And so we just found out, I think last week, that a paper was accepted that addresses this issue where we track not only the pill bottle in a video, but we also track all the parts so that a user can decide what do you obfuscate versus what do you show. So in this example, you can see here the pill bottle is one category we track, and then in there we track institutional information, 3 pieces of RX data, 2 locations of where the name is, and 2 locations of where an address is. And now a user has more flexibility to say, here's what I want you to conceal versus not. So that's one vein where we are innovating. And another is on ambiguity, which in our case means different people can provide different answers to visual questions. So in my initial analysis, I found that approximately half of 450,000 visual questions from 3 different VQA datasets had different answers for the visual questions. And here's just a few examples. In the first case, is my monitor on? Everyone agreed on one answer. But then you go to, does this picture look scary? Who here thinks yes? 1 person. 2, okay, way more. Who here thinks no? Most of you, right? But you have some disagreement, and that's the idea. And if we keep going, you're going to see there's more and more disagreement. And until we started to talk about this, people weren't acknowledging this was an issue. The way the evaluation worked was if a model predicted an answer that at least 3 of the people had given from the 10 people, the model got full credit. So if you have the answer yes to does this picture look scary, full credit for a model. If the model predicts no, full credit, which is fine, but it doesn't have all the information there, which is both can be accurate. So our first effort was to design a model to just predict, is there ambiguity amongst the different people? Our next model was designed to predict how much. Is there only one answer versus are there 10 different answers that you would get from a crowd? Next, we've been looking at why. So for example, it could be because the question has focus ambiguity. What do I mean by that? Well, when you ask, what is the bus number? I'm sorry, I should have moved this a little bit higher, but you can see there's the number 2405 if you squint your eyes and you're a little bit close to the screen. Or you can also see 85A. So it's not clear from the question what bus number refers to. It's not specific enough. Additionally, we can have different answers because of the answers themselves, such as you could have synonyms for how are the water conditions. Subjectivity we already talked about, such as could the floor use a mopping? Some people might say yes, some say no. Level of detail, when you have the question, what book is this? You could just read the title, Maxi Aids, or you could share more information about what's underneath there. Perspective, which side of the room is the toilet on? Well, some people might say the right if you're thinking about standing here, but if you're imagining yourself standing in the room, you might say left, and other people would say center. So it really depends on who you're asking, what kinds of answers you would hear. And then lastly is unanswerable. In those cases, such as what is in this can, often people are trying to be helpful and say from little cues I can make a guess, even though you can't really know for sure based on what's in the image. Follow-up work, based on the observation from our user studies that people often want more detail, was then to provide that. So we've also been we just published a data set that given an image such as of a vehicle, you would add now a decomposition of that vehicle all the way to subparts. So our novelty was to add subparts so that we can get to more fine-grained detail. So you have a vehicle with a wheel, and those wheels are made of tire, rim, and hub. FYI, when I was coming here today, my tire went flat, so then I had a nice gentleman offer me a ride so that I could come and give you this talk. But okay. So like I said, there were 2 key themes that I wanted to talk about, but we've put out a lot of data sets, 22. I think it's a lot. And we track progress with public leaderboards for 11 of those challenges. And the idea is that we don't release the answers to the public. If you release the answers to the public, it's hard to know if someone's cheating or not. We host an annual workshop where we announce winners and we come together as a community to see how are we proceeding, how are things going, and what's still hard. And we have a subset of the challenges related to VisWiz here. Over 280 teams from across academia and industry have participated in our official challenges over the past 6 years. And our dataset publications, part of representing its impact is they've received over 1,750 citations. Most exciting for me to share is that AI now exceeds human performance for numerous tasks, including for captioning images, answering visual questions, and finding salient objects. So the real benefit is coming to people like blind individuals whose lives are being transformed because these models now are doing so tremendously well. Any questions on that before I jump to the next part?
Previously touched on the model for the data set for staff history, how you kind of pull the questions and answers there. Because you don't have these, your trusted annotators answering your questions, how do you handle, incorrect answers or people who maybe are like messing around on the website and either doing answering things wrong on purpose or not on purpose? But are you like cleaning this data set in a way some people have to, annotate having to look visually and check that information, or are you keeping it in there and to add to something?
Great question. So the question is, how do we know when we pull the answers from that Stack Exchange framework that those answers can be trusted? And the way we can know is because Stack Exchange has a really beautiful feature that some of you may have contributed to, where you can upvote or downvote answers. So the community has gone forward and enforced, here's the information we think the general public would benefit from most, and here's where we don't think they would benefit. And so we only leveraged examples where we had that kind of quality control provided from the community. It's a great question, and it's central to how do you build these data sets, is how do you know that you can trust the annotations that you're asking for models to predict? Does that answer your question?
For information that may be missed because it's not popular enough, that people aren't going to get opted, or
yeah,
with the kind of the completeness of the data set, if you are taking out these parts that don't get uploaded.
So I think the question is, how comprehensive is the data set in covering every kind of visual question you could imagine? And there are limitations. So Stack Exchange, for those who don't know, has lots of subsites with different topics. I didn't know this before working on the paper, but apparently there's culture and gardening, there's science, there's under science, a bunch of topics. So you have all these sub-communities that contribute within them. And so I believe we had 151 in our data set. I would have to look at the paper, but it's something like that, where we were able to draw from each of those niches visual questions. And so unquestionably, we are missing things, right? That's 151 topics. If you think about everything you could imagine talking about, it's much bigger than that. So this data set is limited by what are people interested in talking about when they go to Stack Exchange. And any data set is going to have their own limitation. Yep.
So all of the solutions that have been proposed for the challenges, have they all been homegrown academic AI models? Have you compared them to the large models?
Right. So are all the models that are competing on our dataset challenges homegrown, or are they coming from larger entities, larger companies in industry? So industry has been very active with our dataset challenges. The first winner back in 2018, when we announced winners, was Meta. And they were very proud to announce, you had, I think it was Jan LeCun posted it. If you guys don't know Jan LeCun, he's one of the leading minds, right? He said, we won this, the thing, he put it on Twitter at the time. And we've had other industry players since that have won. There's a lot of activity from industry because this is an authentic use case, and therefore they have a lot to benefit. Unofficially, we know of people who are using it that also don't necessarily compete in the public space, but OpenAI, they definitely tested it before they put it out for beta users who were people who are blind in the early years, in the early year. So the dataset challenge is these are very widely used across industry and academia.
The slide which had the prescription model, where you were showing multiple aspects of privacy listed here.
Yeah.
You said that the user has the choice of what to share or disclose. Who is the user?
Okay. So in this case, it would be someone who is blind, who is asking, there's different scenarios that you can imagine, okay? One scenario is you are a company, such as Be My Eyes, or Microsoft, who has their own app, or Google, who has their own app, Look Out and Seeing AI. Many companies offer the ability for blind users to use their phones to learn about information. And some of those companies are recording all this information because they want to do things like license that data for use by others to train their models. And so there's a real ethical question for these companies of, when we have this data, is it okay to give it out knowing that there is so much private information? We know from the VizWiz data set, which is only 45-ish thousand examples, that 12% of that is private information. And these companies they have millions of examples, if not more. And so this could help these companies make decisions about what categories would you obfuscate because we localize information versus not when they define here are the categories. That's one pool of users, but then you have the other users, which is I am a blind person, I collect this video and I want to submit to a person because I want verification from a human being, not AI, because I don't trust AI is the argument. And I, as a user, before I push that out to my audience member, can say, when the model tells me I've detected this, here's what I've detected, the user can go through and say, I want to hide this and this and this. Okay. Yes. Yes.
Got one from Murad. He's asking, how do you handle the curation of data sets that are outside of your lab's domain expertise?
So the question is, how do I go beyond, when I curate a data set, how do I support going beyond domain expertise? And I will touch that in the next portion of this, but much of my work is interdisciplinary. I am very much into collaboration, and when I was a PhD student, I would collaborate with the biomedical engineers and I built data sets with them. And then I collaborated with Jeff, which opened me to a whole an entire world of people who are involved in accessibility. And so a lot of my work is through collaboration with people who are in the domain. You said there were a few questions? Yeah.
What kind of data augmentation is done for these data sets?
Oh, interesting. So the question is about data augmentation. So we let the data sit as it is because primarily what we're trying to do is put out tests. And so we're not going to augment it. But I know from the teams that have been competing on our challenges that many of them do a tremendous amount of data augmentation, as simple as flipping images, vertically, horizontally, changing the coloring. Yeah, there's a lot out there. Like I said, there's been over almost 2,000 citations on this work. People are doing a lot of different variants on data augmentation.
With respect to the ambiguity problem,
Mhm.
is there also information collected about how other students might ask clarifying questions about the information, like ask for re-prompting, like for the tuna can, or questionable unanswerable can, like rotating around to be able to answer the question? Is that maybe information that's available, or is it to be a part of the challenge?
Yeah, so the question is, once we learn there's ambiguity, how do we resolve it? How do we help the user resolve it? And good news that I was going to share at the end of this talk is that the National Science Foundation decided to fund us to explore that question. So that's in progress. So you have a NSF-worthy idea. Okay, so I'm going to go ahead and jump through. Good news is the next two sections are going to be shorter because I assumed we'd be a little bit tired here. So I'm going to go next through humans in the loop for practically useful results. And so this is really thinking about improved representation and efficiency. Sponsors of this work have been Microsoft, Shan Zuckerberg Initiative, UT Austin Good Systems, and NSF. And the two ideas that I want to talk about when thinking about humans in the loop for practically useful results is, first, who decides what to build? Oh, that's cute when she said pick me. And then how and when should humans contribute to visual analysis? And so those are the two key themes that came following some of the initial data sets. And so the first contribution of our work is addressing an AI developer problem. And this relates to one of the earlier questions that was just asked, which is the answer I gave is I collaborate. A very well-known problem for us AI developers is that we focus and become experts on one thing. We become really good at segmentation, or very good at classification, or very good at tracking. And we come up with that one hammer. And we say, I've solved the world's problems. And we go around trying to hit everything with our one tool we have. So here, this is not a nail, this is a screw. It's not the right fit. But that's what often happens. A lot of my work is motivated by real use cases, and I authentically want to make a difference on what happens for those real users. And so following some of the data set creation that we had done, particularly when the instigators of a whole stream of work was looking at how the captioning models were making predictions. And the captioning models that were being created based on what we collected were captions that came from people who maybe didn't know anyone who was blind. So just as a sample, who here knows someone who is blind? So if you look around, almost no one here knows someone who's blind. And if you think about that, Then think about when you go to an audience that does crowdsourcing and you ask them to write captions. Likely they don't know how to describe something that's useful. As an example, there's a picture of someone wearing a green shirt with text, and the caption describes that. It says it's a green shirt with this text written on it. But then you look at the question that was asked when you bring that into the picture. What the question is the shirt dirty or clean? Right? And that's very useful. So that's just an example to highlight a broader trend, which is we really need to go to our target users to find out what information they want for these different kinds of tasks we're trying to support. And so we did that. Actually, I brought in, when I was at UT Austin, as a postdoc, Abby Stengel, who actually finished her PhD here under Tom Ye. And she really pushed this forward. And some of the themes that came out of our research when interviewing people who are blind is things like, we need to move beyond one-size-fits-all image descriptions, which is what models do. For example, if you have different scenarios, such as you're going shopping versus you're trying to navigate somewhere versus you're searching on the internet, you have different interests of what kind of information you're looking for. And accordingly, the captions need to be written to acknowledge the context of where you are encountering these images. We also found from another study that I mentioned earlier that when we asked people who are blind what kind of answers they wanted to visual questions within the VisWiz dataset, most said they wanted longer answers. And then we did quite a few studies on providing more privacy preservation tools for users' shared images and videos. They want it. They have to make a choice between I can't see my surroundings and therefore I need to be vulnerable to give up information about my visual surroundings versus I need the answer to a question to help me in my daily life. Therefore, I will take the risk to share my private information so I can get that visual assistance. And so those are some of the themes that we've explored in trying to let the target users of AI decide what to build and then bring those ideas into the AI world so that we were actually meeting the real target users' desires. And the second thread is about how to ensure we collect high quality results while minimizing human effort in doing so. So question for you, how many of you have done a task where you've looked back and you said, wow, that was really inefficient how I did it. I wish I would have done it differently. Almost all of you. For the rest of you, wow. So going through some rounds of crowdsourcing, I started to realize we were doing lots of things inefficiently. And so there's this body of work that's saying, how could we do it better? Knowing what I know from having done it less good the first, second, third, fourth time. And so one body of work is human AI workflows that leverage the complementary strengths of humans and machines. Another is creating AI that checks other AI's output work and then identifies when it makes mistakes and recruits humans to come and fix those mistakes. Okay, so we only bring in humans when we think that a mistake was made from the AI, and then also AI that collects enough annotations to capture a crowd's intelligence, because previously the paradigm was one size fits all. We have one correct answer, let's predict that. We need to make sure we get all perspectives when we build these data sets, is the argument that my team made, and so we started to collect as many annotations as we needed. We explore these problems, the human AI workflows for segmentation, detection, classification, and captioning. As far as AI that checks other AI's work, we did this for object segmentation and tracking problems. For AI that collects enough annotations to capture a crowd's intelligence, we did this for visual question answering and salient object segmentation. And then related to this last topic, we also developed AI that tells us when we shouldn't even bring in the human in the first place, such as asking someone to caption an image when the image content is unrecognizable. So we made a detector that can recognize something. If it's an image, does it have any content that's recognizable? If not, let's not even bother doing annotation. Don't give it to a human. Like I said, I'm going to make this section and the next section short and sweet. So are there any questions on this section before I move to the next one? Okay. So next step is going to be efficiency and thinking about resource saving methods for less costly, faster AI training and inference. And the sponsor of this work is Adobe. I've been collaborating with them now my team's collaborated with them for 7 years. So it's been a really long, lovely journey with them. And so the ideas that are gonna sit in this in this third part of the talk are twofold that center on how do we accelerate AI development as well as AI inference. And so the first theme is how do we go ahead and support more tasks? I've already talked to you about this paradigm of creating data sets. I talked about it in the realm of having to create these tests for AI. But we also need often to create data to train the models in the first place, to teach them how to do something. And relying on humans is hard because you have to find people who'd be interested to come and do that task for you. They have to be interested, and therefore you have to maybe pay them or incentivize them through their goodwill that they think they're doing a service to humanity. Whereas you can synthetically create many people, such as holograms here, right? And that's kind of the intuition, that's an analogy that we explored, is how do we scale up the amount of training data we collect? And in our case, we will be doing that automatically. The other theme that I will touch on is this idea of how do we create lightweight, fast models by compressing existing models. So we can have this really heavy, slower elephant compared to a lightweight, but very fast hummingbird. And that's the idea. We want to go towards that hummingbird that can go really fast and be very small. So as far as the first contribution, this requires just a little bit of background in machine learning. Who here has taken a machine learning class of some form? Almost all of you. So just a quick recap. Hopefully you know this. You have your training data and you have your test data, right? We already talked about the test, but we need training examples such as you have an image and a label saying this is Harry. An image and a label, image and label, image label. This is a binary task of predicting is something hairy or not hairy. And so the scope that this body of work is on the training data and how do we scale up collecting that training data. The first task we explored this for was on the task of inpainting. Given an image, we want to remove something and replace it with something else. So the earlier work that we did was we automatically created training examples by taking the original image, taking that red region, and pasting it on another image to mix the information. So we're kind of corrupting the content. And then we paste it back into an image. And then we also have the region between the green and the red, where we just take totally random information from another image. Okay, and so we basically corrupted the original images, and then we trained a model that, given the new corrupted image, it had to recover the ground truth. Okay, so it had to recover the original image after we corrupted that information, and we need both of those pieces to be able to do that correctly. After that body of work, we explored another idea, which is how do we figure out, instead of getting things that look similar like another cow in the field, how do we find other plausibly relevant information that we can put in there? And so what we did is we said, okay, given an image where we remove something we want to replace, we looked for other images that had similar context and pulled it out. So we looked for similar images, and then when we went and we grabbed the annotated objects that were already there, for those that are familiar with them as COCO dataset, that was what we used because they'd already annotated objects. And then we took each one of those objects and we were able to paste it in the context and use that as training data. So we artificially inflated the amount of diversity that could be found. Turns out that these worked well and both bodies of work were published, and extending that, we just, this past year, continued on this simple idea of just use what's out there. And so we focus on how do we make stickers that have parts on them. What do I mean by a sticker? You have something that's very clear on a blank background. You can imagine just pulling it off. Okay? And we were focused on how do we do that for not only objects like a dog, but parts such as a tire of a car. I feel like the theme of tire is just coming back to me today. But a foot of a lizard, a head of a tyrannosaurus, a flower of a lotus. And these are actual results from our model. Okay, so it did much better than the other models that existed, and the training is actually quite simple. All we did is we went to existing data sets where people had annotated parts, and we pulled those out of the images and we put in a gray background. And then we trained a model to, given what was the part we pulled out, such as a head of a green lizard, we then used LoRa to go ahead and update the model so that it would be able to create stickers. Okay. Next and final theme for this talk, creating lightweight, fast models. Background knowledge of this, the background of this is knowledge distillation. So the hope is that when you get a teacher, they can take their vast knowledge base and distill it down such that you can comprehend it. Who here has had experience where you have had a teacher successfully distill complex information so that you could understand it? Who here has had this situation where you've had a teacher try to do that and fail miserably? Okay, so that's the challenge we have, is how do we do it effectively? And so the idea that was proposed originally was we want the students' predictions to match the teacher's predictions. So this is a softmax, if you're familiar, which many of you are familiar with machine learning, softmax output. We want the probability distribution that a teacher predicts to be passed on to a student, where a student can accurately mimic the teacher's predictions. And the idea is that when we train the student, we are going to pass the information of the teacher to the student, which is going to have a smaller number of parameters. Much of our work was on the task of style transfer. Given an image, take on a new style. This is an autoencoder. Autoencoder takes as input. It's a model that takes as input something and it outputs itself. Take a picture of me, put it in, it should put that picture out of me after compressing it to some feature, and then it decodes into a more compact feature, and then it encodes to a more compact feature, and then it decodes to a image again. And so the magic here is that it turns out that when we encode the incoming information, we can easily separate features that capture the content and the style. And the magic of that comes from models that are trained to do image classification. Because the classification task is just about, can you detect what content is an image? Is it a car? Is it a person? So those already do that for us. They detangle content from style. So that was the intuition of the pioneering work, is that you can take the content information and put it with style from another image, and you can put that together and decode to get a stylized image in the style you want. Subsequent work, not from my team, said, well, to do it better, to get more detail, it's kind of like the way that I teach, and my sons and daughters' teachers are teaching them how to draw. Most of my sons, he's 5, is you teach someone first draw a circle, right? So that's our first layer. And now add more details. Now put in the style of eyes and a mouth and a nose. And you just keep going to finer and finer grade style features. That's just for intuition. It's not exactly like that insofar as what is being done at each stage, but that's the idea, is that you use a cascade of autoencoders to keep fine-tuning the content to get finer and finer grained style details. Our observation was, this is really clunky and it's overkill. It's very parameter heavy. It's like that elephant. And so our idea was, let's go for a lighter weight single pass model. So instead of doing all of this, we said, okay, let's encode where we can have these operations all sit in one autoencoder. And then once we were able to get that into one autoencoder, we then said we'll use knowledge distillation such that when we go from the encoder to the decoder to come up with that stylized image, what we're going to do is we're only going to distill out 85% of the style information. So it's more compact. So you can use PCA to say, here's the style information that's more large, and we're going to make it more compact, and that's what we'll pass down to the student. And then encoding is just as it was. Compared to existing models at the time, the distilled model variance ran 5 to 20 times faster, with at most 1% of the original parameters, while yielding better results. We've had follow-up work. We have something that was just accepted at a workshop at NeurIPS, where we distilled state-of-the-art models for image classification, and we achieved state-of-the-art performance. And the idea was, we need to intelligently figure out which teacher layers should be distilled down. And when we train, we also need to limit trying to get the information about predictions back propped to the student backbone. So, summary, from data to deployment, empowering people, the goal is to empower people with more inclusive, practical, efficient AI-based solutions. And hopefully I've convinced you that we've done some of that and inspired you to continue on. And we've done that through dataset challenges for more inclusive models, humans in the loop for practically useful results, and resource-saving methods for less costly, faster AI training and inference. There are a tremendous amount of people who have contributed to this. I'm going to put them up here. There's my current mentees, my former mentees, the many people who have given me their time as collaborators, thousands of crowd workers, maybe even tens of thousands, I'm not sure. Creators of the original VisWiz application and the evaluation servers that we've been using for many years, and then also the funders. And I'd like to just do a quick spotlight. It's been a really profound experience for me to look back at the work that my team has done since I became an assistant professor. And I just want to make a shout out to my advisor, Margaret Baker. She just passed away about a month ago, and so it was really timely for me to think about the work I did and think about her. And I just want to say that if you like my work, this woman was a huge part of what I'm presenting today, and I continue to carry on the story that she put in me. So what's next? I'm a twin. I'm an identical twin, and I think everyone should have a twin. And we don't have those yet, but you can imagine the many benefits that might come. And so two we've been exploring in my group. One is to help with radiation treatment. If you can create an avatar of a human that's going through treatment, add in some breathing motion, you can all of a sudden do better at targeting where the radiation goes to only kill tumors and not kill healthy tissues. And that's going to have great health impact, and that's ongoing work we've been working on for 3 years with people who actually do the treatment. I also mentioned the work on compositional scaling so we can decompose objects, and that's going to continue. And of course, if you can do that well, you can get very highly detailed digital twins. Second was a question I got earlier over here that I said it's an NSF-worthy idea, the idea of having ambiguity-aware solutions, where if you have a question such as, what is the cleaning product, which was asked by a blind person, being able to give the right answer, such as you could have citrus spray and wipe, Dawn dish soap, Windex window cleaner, and making sure we don't have someone use Windex window cleaner to clean their dishes, right? And so that involves creating data sets, understanding the target audience's interaction preferences, and designing efficient models. And then our last body of effort is expanding who we've been supporting in the visually impaired community beyond people who just have ocular vision impairments, which is an injury to the eye. That is the reason they struggle to see, to also include people with cognitive impairments, which can result in many different ways of having difficulty seeing. And so this is actually largely inspired by my graduate student who had traumatic brain injuries. He says I was allowed to share this, so I'm sharing it. But he had traumatic brain injuries, and he suffered with sight because he originally had all of his brain to use in navigating the world, and all of a sudden part of his brain couldn't contribute. So he was getting stimulation overload. And so for him, if we could somehow reduce the incoming information to be a smaller amount of stimuli, it would enable someone like my student, when he was, before he was rehabilitated, to be able to function and go out and live his life normally. And then there's also, from cognitive vision impairments, other kinds of injuries. There are people who lose, because of their brain injuries, the ability to see, half of the room and much more. And so there's a lot that could go into that realm, and that's another future wave of work we are doing. And that is it for my talk. Thank you so much for your time, and I welcome any questions. Yes.
While you were speaking, they asked, do you also use computer graphics to create synthetic data sets?
So the question is, does my team use computer graphics to generate synthetic data sets? And the answer is we have not yet. There's promise there, but that's a harder thing to do than what we've been doing. Pretty low-hanging fruit kind of things. It's been pretty easy what we've done, I would say. And so certainly you could go to computer graphics, but that's going to be more challenging for many reasons, including you need to understand how to create yeah, I'm just gonna say it's more challenging. I'll leave it at that. Yeah. Any other questions? Yeah.
In scaling up your data set that you were describing, do you face any issues that are analogous to what I hear with generative AI models where you train them on a data set, they go to produce data, they get trained on the original data plus the data they produced, they get in danger of model collapse?
Yes.
So they're training on things they themselves generate. Is there any danger of that with what you're doing there in scaling up data sets?
So the question is there any danger in generating data off of models that we create and training on both of those sets? And the answer is yes. How you use the data you have in training as a whole body of work, there's things like curriculum learning that my team is currently exploring for hopefully a paper submission in November. But kind of like how we create a curriculum to help students go through the classroom, the idea is we similarly create a curriculum for which examples we show to the student over time. And so that's part of it, I think. But then the other part is there needs to be some way of, yeah, I think that's a major problem. And I think much of modern AI is struggling with how do we leverage the synthetic data, because of the fact that we are, at least at the industry level, seemingly we've used up all the data that's obvious, which is on the internet. And when we don't have that, how do we continue to make progress? And so we are turning to synthetic data. And so that's a very, very front of the wave question. Mm-hmm.
So when you talk about the twin, so what is your thought about like the physical AI stuff?
What's my thought about physical AI when you said the digital twin? Can you tell me more about what you mean by physical AI?
Find the report. And sometimes, like for example, for the robot, if the robot acting wrong, probably you will cost a lot of money. And then so I think one of the physical AI goal is trying to duplicate the real world.
Yes.
Scenario. So do you think that it is like correlation to that, or I mean your digital twin?
Yeah, the digital twin task is very difficult. I just kind of lightly said, okay, this is what we're doing. We get training data, but the data we're using is 2D. Currently it's images, and we're talking about trying to model the 3D world. So being able to make the steps so that we can have digital twin representations like what we have been doing in the medical imaging scenario, which are 3D representations. It's a big step, and it's going to require different ways of, I believe, data creation for training. And so the computer graphics question that was asked earlier might be a way to go, because in computer graphics, it's easier right now to get these 3D worlds, but maybe also there'll be some progress on sensors as well, where we can more effectively get that kind of data. Yep. Does that answer your question, or is that, yeah. Okay. Yeah.
The chat, we also use VLM for digital twins.
Yes. So there's a puzzle face to the question, which is, do you also use a VLM for digital twins? VLM, for those who don't know, is a vision language model. So if you go to some models, they only speak using language. You can only communicate with text. A vision language model can also interact with visual information. Images, I don't know to what extent. Videos, I don't think videos are much in there, if at all. And so as far as doing that for digital twins, certainly parts of our work, the compositional decomposition, the decomposing objects, we do use VLMs. Turns out that they are very poor when it comes to getting subparts and even parts. And so they have a lot of progress that they need to become actually practically useful. So we have one more minute. I will be happy to stay after for questions, but is there any final question before we end here? Yes.
So I'm curious about how you think of bias and ethics in the context of, and so some of the examples that you gave, for example, being able to drop different images into context can be used for fun and playful things and can be used for deep fakes with potentially very grave consequences.
Yes.
Like, how do you perceive those kinds of issues all the way back to the like curation of data sets?
Yeah, so bias, the question is about the ethics and the biases that these models have. And I think that models are always going to have biases. That's what they are, right? They're learning from data, patterns, and they will embed some kind of bias. And the hope is that the bias is more accurate to reflecting the way we want them. And so for me, I'll just give one example of a way that I think the techniques that we've talked about can benefit, and that's on the synthetic data generation, which is currently models are really good with text, with language. When they crawl the internet, that kind of data is very prevalent and it's much easier to collect and learning is going much better. On the vision side, it's not going as well. And models are prone to going to their language biases to make predictions. Historically, it would look like, what color is the banana? And the model would always say yellow, even though bananas can be other colors. And so I think that it's important when we develop models that have multiple modalities, where one modality performs worse than another, such as vision, that we can break the biases by doing things like changing what is typical synthetically. So automatically coloring bananas to be different, but it can look different than that if you make compositions of structures that have things you wouldn't traditionally see, like replacing a hand with scissors. So I think they're always going to have biases, and it's very sad. And my hope is that I help us move more and more towards a grounded reality that includes everyone. But I know that that's an aspiration and that there's always going to be a limitation. Does that answer your question? Okay. Well, I think it's time, yeah.
Thank Dr. Gurari again.
So you got it?